Charge on colloidal solutions. So as I told, colloidal particles are carrying charge. Particular colloidal solutions carry particular charge only. Means colloidal solutions either they may carry positive charge or negative charge. So here in examination, how they are asking among the following, which is negative colloidal solution, among the following, which is positive colloidal solution, like that they are asking. Colloidal solutions carry charge. So now positively colloidal solutions. Positively charged colloidal solutions. Positively charged colloidal solution means once if they form colloidal the solutions, no, they absorb, they acquire charge from electrolyte. So based on the preferential adsorption, they get positive charge, negative charge. So once after the formation of solution, sometimes they may absorb positive charge or negative charge on its surface. So based on that, they acquire positive or negative charge. So here, example for positively charged colloidal solutions. Hydrated metallic oxides. Hydrated metallic oxides. Examples if you take aluminum oxide, Al2O3, it is a dihydrated one. It is a positively colloidal solution. Next one, iron oxide also, Fe2O3, H2O. Is also next one, hemoglobin. Hemoglobin, etc. are the examples of positively colloidal solutions. There are negatively charged colloidal solutions. Negatively charged colloidal solutions. Metal salts, example gold salt, copper salt. So are the examples of metal salts are the examples of negatively colloidal solutions. Example, copper salt, and metallic sulfides also. Metallic sulfides, example, arsenic sulfide, cadmium sulfide. Cadmium sulfide are the examples of negatively charged colloidal solution. Starch is also an example of negatively charged colloidal solution. Negatively charged colloidal solution. Just one example I'll give students how they carry positive and negative charge. Actually, it is beyond your scope. If you are able to understand, it's good. Otherwise, leave it. Now, what I am going to explain. This one is important. You have to. This you have to prepare. Here, types of colloidal solution based on charge. Here, colloidal solutions carry charge. I said same colloidal solutions carry same charge, either positive charge or negative charge. Examples of positively charged colloidal solutions, negatively charged colloidal solutions are given. Next one, how they carry charge. For that, I'll give one simple example. If you want, you keep it in mind. Otherwise, leave it. If you do not understand, also it is not a problem. Suppose here AgNO3 forms AGI. AGI. This formed AGI is there, no, it will absorb negative charge. Absorb negative charge. Suppose if means here AgNO3 is the dispersed phase, Ki is the dispersion medium. Means dispersed phase AgNO3 we are adding to Ki. Here Ki is more, AgNO3 is less. So after forming AgI, it is absorbing I minus. So the resulting solution will get negative charge, students. This anyway neutral, it is absorbing negative ion from the solvent or dispersion medium. So it is a negative colloidal solution. Next, suppose Ki, if Ki is the dispersed phase, AgNO3 is the dispersion medium. Here also AgI will form, but this formed AgI will absorb Ag plus from the dispersion medium. AgI from the dispersion medium. So the resultant solution will become positive. So in this way, based on the preferential adsorption of solution, they get charge. Differential adsorption. I minus AgI, I minus AgI, I minus. Again, they I minus form, no? Again, you try to take Ag plus, Ag plus, Ag plus. It will absorb. Ag plus means there is a negative and positive charge. There is a double layer. Again, upon this, one more layer will develop. This is called Helmholtz layer. When positive and negative charges are interacting each other, there will be some potential difference. Let me open. There will be some potential difference. Little potential difference. That potential difference is called zeta potential. That potential is called zeta potential. When negative ion and positive ion, if they are interacting each other, so there is a difference between the positive and negative charge. That potential develops between positive and negative charge. That is called zeta potential. Zeta potential. If zeta potential is more, stability of the colloidal solution is more. Means colloidal solutions, they must carry charge. If they are losing charge, means they are losing their identity. So they settle like suspension. So they must carry charge. If they carry charge, there will be a potential difference. If it is more, magnitude of charge will be more, stability will be more. Okay, students. So zeta potential, that the potential difference developed between the two layers is called zeta potential. Zeta potential is directly proportional to stability of colloidal solution. Stability of colloidal solution. Zeta potential is directly proportional to stability of colloidal solutions. Next, one more property is the color property. Sky appears blue. Sky appears blue. Why, student? Because it is in blue color. What is the reason? Why sky appears blue?
The particles only scatter blue light.
Very good. The particle present in the air or atmosphere scatters the blue light, so that blue light reaches our eye, so it appears blue. So color of the solution, color of the solution depends on wavelength of the light scattered. What is the first factor, students? Color of colloidal solution depends on wavelength of light scattered. Wavelength of light scattered by dispersed particles. Right now. Second property, that also depends on size of the colloidal particles. Size of the colloidal particles. So even gold sol particles also. As the size of the gold particles changes, no, color of the gold also changes. Color of the gold sol also changes. As size, if it is more, it appears in blue color, red color, finally it converted to golden color. As the size is when the size we minimize, no, up to certain stage it appears in golden color. So it depends on size of the colloidal particles also. Next one, color of the colloidal solutions also depends on the direction which the observer receiving the light, the way he receives the light. So there are two types. One is reflected light. We can observe the color. We can get the we can see the color through reflected light. Another one is transmitted light. If the observer is receiving the reflected light, color will be one direction. Color will be different. It appears in one color. If observer receives the light, transmitted light, color will be different. So the way he receives the light also. So color of the colloidal solution depends on transmitted and reflected light. And the direction. Otherwise, I'll use reflected and transmitted light. Okay, these are the main factors. Particular color, the colloidal solution, the color properties. So we have finished electrical properties, Brownian moment, Tyndall effect, charge on colloidal solution. Next one, color of colloidal solution. Next one, coagulation. 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 Anyone, can you tell students what is coagulation? What is coagulation? Do you know, students? Coagulation is nothing but process of settling of colloidal particles. Coagulation is nothing but process of settling of colloidal particles. Coagulation is nothing but process of settling of colloidal solution. Means they are losing charges. Yeah, Stevani, correct. Is called coagulation. How to coagulate this one? Colloidal solution. There are certain methods. By using those methods, we can coagulate the colloidal solution. First one is, suppose here colloidal solution is carrying negative charge. We have to neutralize the negative charge. To neutralize the negative charge, what we have to do, students? We have to add a negative charge, right? To neutralize the negative charge, we have to add a negative charge. Isn't it? Tell me, yes or no? Yes, Sandra, correct. So to neutralize negative charge colloidal solution, we have to add positively charged colloidal solution or positively charged electrolyte you can add by mixing two oppositely charged salts. By mixing two oppositely charged salts we can utilize. That is the first. Coagulation can be done by the following methods: by mixing, charged salts. Second one, by boiling. If you boil, there are some interactions. These colloidal solutions, dispersed phase particle, dispersed phase particle, they undergo continuous collisions among the dispersion medium particles. Some collisions will be there. At the same time, they collide with the surface, with each other, and they collide with the surface. In that moment, they lose charge. So boiling is one more technique to coagulate the colloidal solution. And before this boiling, I wanted to give one more information about this mixing of opposite charge. See students, As2S3. As2S3. Is it negatively charged colloidal solution or positively charged colloidal solution, students?
Negatively charged.
It is a negatively charged colloidal solution. It is a negatively charged colloidal solution. To neutralize this, what we have to do, students?
Add positively charged.
We have to add positively charged salt or any electrolyte or any ion we will add. Suppose here it is a negatively charged colloidal solution. Na plus I am adding means NaCl, MgCl2, AlCl3. Which one can coagulate the above colloidal solution faster or effectively? MgCl2 or AlCl3 or NaCl? I want to coagulate. Very, very important for competitive exam. Right now, coagulation power is directly proportional to valency of coagulate ion. This is also called fluctuating ion. Next one. So coagulation power is directly proportional to valency of the ion. To coagulate, I'll give one positively colloidal solution. Al2O3 XH2O. It is a negatively charged colloidal. I want positively charged. Yeah, positively charged colloidal solution. It is a positively charged colloidal solution. So if they give order like this, FeCN6 4 minus, PO4 3 minus, SO4 2 minus, and Cl minus. See students, here magnitude of negative charge increases, coagulating power increase. This is only Hardy Schultz rule. So this is about charge on colloidal solutions. Colloidal particles carries charge. So we can neutralize this charge by adding oppositely charged salts or oppositely charged by adding electrolytes. Also, we can make it neutral. So while adding electrolytes, we can see the effectiveness when magnitude of charge or valency of the ion is more, coagulating power is more. Suppose if you take 1 mole of FeCN6 4 minus, it can neutralize 4 units of positive charge at a time. 4 units of positive charge at a time. So it is more effective compared to PO4 3 minus. It can utilize only 3 units of positive charge at a time. And SO4 2 minus can utilize only 2 units of positive charge. Cl minus only 1 unit of positive charge. So that coagulating power decreases. Next, this is about boiling. I already said, no? Boiling. So when we boil, molecules of the dispersion medium collide with each other. After some time, they lose charge. So boiling is one method. Next one, electrodialysis. Electrodialysis. See students, here one beaker will take this. This is like membrane. It allows only solvent particles, not solute particles. When electrodialysis means when we electricity means positive and negative charge, we will keep no electrodes. Negative charge. When these colloidal solutions carry positive charge, they move towards negatively charged electrode. If they carry negative charge, they move towards positively charged electrode. So when we pass electricity, negatively charged colloidal solutions get attracted towards positively charged electrode. If the colloidal solutions carry positive charge, they move towards negative. If they carry negative charge, they move towards positively charged electrode. They move towards oppositely charged electrodes and they get settled. This is electrodialysis. So colloidal particles move towards oppositely charged electrodes. Oppositely charged electrodes. Oppositely charged electrodes. Electrodialysis. Next one, ultrafiltration. Ultrafiltration. Ultrafiltration is nothing but filtration only. So if we use normal, why we used ultra? If we use normal filter paper, even colloidal solute particles also can escape. Not only solvent particles, solute particles also can escape. We are separating solid dispersed phase particles from dispersion medium so that they can settle. Here, ultrafiltration while doing why we are using ultrafilter paper. Suppose here normal filter paper are having this type of holes, little bit. So through these pores, even solute particles, dispersed phase particles also can escape. We want only solvent particles pass through this filter paper. For that, what we do know, for this filter paper, they dip in collodion solution. Collodion solution. Collodion solution. So here, collodion, when we dip it in collodion solution means what is collodion solution? Nitrocellulose solution. Nitrocellulose solution. When we dip it in nitrocellulose solution, this pore somewhat occupied by this collodion solution. So that size of this pores decreases. Whatever the filter paper we prepare now like this is called ultra filter paper. Ultra filter paper. Compared to normal filter paper, here size of the pores decreases. So that only solvent particles move. So in this way, applications of colloids. Some few applications are here. Applications of colloids. One is Purification of drinking water. So here, suspended impurities, when we add alum, it absorbs impurities from the drinking water. The suspended impurities will be absorbed by this alum. Impurities, one thing. Next one, electrical precipitation of smoke. So here we can control the pollution by doing this one. What do you know? Or this smoke chimneys are silencer will tell no. So from chimneys, different types of gases will evolve during the combustion. If the chimney or that pipe is there, no, if we keep some uh, charged plates means impurities. If they carry positive charge, we have to keep negative charged plates so that they will be coagulated over there only. Be coagulated. Those impurities will be settled. We can control the pollution in that way. Carbon, arsenic, dust, and all. Before they come out, they get they move towards oppositely charged plates and they get coagulated. So in that way, we can control the atmospheric pollution. Third one is tanning. I think you had in 10th standard, 9th standard. What is tanning, students? Tanning of leather. Generally, animal hides and all they carry positive charge. Those are the examples of colloidal solutions only. Leather coloring and dyeing is one thing. And when we add this tannin solution, this leather will become hard, because this tannin has negatively charged particles. It is a negatively charged colloidal solution, so mutual coagulation takes place. So leather will become hard. Tanning of leather. Then now you can read also. And at the end, students, it's anyway finished. I want to give one more important small topic. Just it may finish with 5 to 6 minutes. Types of adsorption. Only adsorption I taught. Types of adsorption important for competitive examination. Types of adsorption I'll use. Actually, in the beginning, it is not in this material. I am giving extra this one. Types of adsorption. Types of adsorption. But tomorrow you have test on this same chapter. So 10 to 15 minutes I'll give time. You just refer. If you get any doubt, you can ask today itself. Types of adsorption. There are two types of adsorption, student, based on the force of attraction between dispersed phase and dispersion medium. Dispersed phase and dispersion medium. One is physisorption. Or physical adsorption. Another one is chemisorption or chemical adsorption. In physical adsorption, name itself we can make out, student. There is no chemical bond between dispersed phase and dispersion medium, just physical force of attraction. That force of attraction is called van der Waals force of attraction. Van der Waals force of attraction. Right now, no? Dispersed phase and dispersion medium. Sorry, adsorbate and adsorbent, you write. Here, adsorbate and adsorbent attracted by physical force of attraction. In bracket, van der Waals force of attraction. Force. It's called van der Waals force. Here, adsorbate and adsorbent. There must be chemical bond. So this is Physical attraction, no, is physical force, one-to-one force. Here, chemisoption. According to you, which is selective, students? Which is selective? Selective, no. Which is specific in nature? Which is more specific in nature? Physical adsorption or chemical adsorption? Specific means particular adsorbent only can combine that specific nature in which we can see more in physical adsorption or chemical adsorption. Sandra, correct answer. Chemisoption, because chemical bond happens between selected reactants only, not among all. Okay, so physical adsorption means that one-to-one force of attraction can happen anywhere in between any molecules. Okay, so this is least specific. So least specific. This one is highly specific. Both are exothermic only. Both are exothermic. Once particles before adsorption, particles are free. They are having more energy. Once if they get adsorbed on particular surface, they lose that kinetic energy. They lose that energy. Means they are losing energy. Means the process is exothermic. Is highly exothermic. Exothermic. And during physical adsorption, see students, this is the surface. One time adsorption took place. Again, upon that, one more layer will form because it is physical adsorption. So multi-layers can form. During chemical adsorption, there is no multi-layer formation, just product formation takes place. Chemical bond, no. So one more layer, it won't. This will attract one more sun in physical adsorption. So physical adsorption is a multi-layer process. Layer process. This is mono. Next one. It happens at low temperature. It happens at high temperature. Okay. These are the basic differences between physical adsorption and chemical adsorption. Physisorption and chemisoption.